So we're going to finish up with formal charge since the bell rang on us the other day. So basically, formal charge is a way that you can calculate or try to guess which one is the most likely structure. Okay, and so we're going to do an example with our sulfate ion here in a second, and then we'll maybe hopefully that will make it a little bit more clear. So I think before we ran out of time the other day, we said that this right here was supposed to be 1/2. So make sure everybody made that correction. So it's supposed to be your group number, and then you subtract the number of lone electrons. Remember, they belong exclusively to that atom, and then half of the bonding electrons. And the reason it's half is because when it's sharing a bond, half belong to it and half belong to the other one. So that's what we're going to do. Okay. So let's look at that example of SO4 and just see if it makes sense. Hopefully it does. Okay. So I'm going to have to, it's right here is where the example is, draw all the possible structures for the sulfate ion and decide is which most plausible. I'm going to put a new sheet because there's no way I can draw it in that small space. It's just not happening. Okay? So sulfate is SO4 minus, 2 minus, excuse me. So how many total of electrons are we going to need in our Lewis structure? 32, because we had to add 2 electrons for the -2 charge. Okay, so first way we're going to draw it is just put 4 oxygen on there, and then give everybody their electrons. Okay, and when I do that, remember we do the brackets, and we say 2 minus. Okay. And if I count all those up, they should have all of their electrons, okay? But another way that you can draw this is actually where you can double bond. And then he would get his, sorry, my electrons, I'm electron challenged, lone pair challenged. And then this would have a 2 minus also. Okay. Now, this particular structure, I'm going to put an asterisk by it because it would have all of its, it would have all the resonance structures that would go along with that. Like how do you know whether to put the 2 bonds there or somewhere else? We're not going to draw all of those because the fact that they would have 2 double bonds and 2 single bonds, all of their resonance structures would have the same formal charge. Okay. So you don't have to, we're not going to draw all those out. Okay. So now we're going to calculate our formal charge, and when we do that, we're going to calculate it for both the sulfur and the oxygen. Okay? Okay. Both are in group. They're in group 16. But remember the old style way, okay, is 6, like that would be A's and B's, so that would be group 6. We're going to call it group 6. If you look at the periodic table, have you ever noticed that, where sometimes they have those and then they have the Roman numerals, and there are 6 A's, and the ones in the middle are the B's. That's just confusing, okay? But another way to do this with the main group elements, which are S and P, is their valence electrons, because group 6 has, right, 6 valence electrons. So we're going to say 6 minus, okay, how many bonding electrons? It doesn't have any lone pairs, okay, right? So how many bonding electrons does it have? 4. It has 4. Because it would be 8 total that it's sharing, but half of them belong to it. So 6 minus 4 is a plus 2. And for formal charge, the closer to 0 that you can get is better. Okay? But then you still have to have everything add up to 0 or have that charge. So our sulfur in this case is going to be a plus 2. Okay? Now let's look at oxygen. Also 6 minus how many lone pairs does each oxygen, or how many electrons does each oxygen have? 6, okay. And then how many bonding pairs? -1. So that means that all of the oxygen, in this case, because they're all bonded the same, are going to be -1, -1, -1, -1. Okay? So what's my total charge going to end up being? Add up my positives and negatives. -2. So those are good. That's a good structure because it adds up to the -2 that we need right here. Yes?
Why is it
Oh, because 6 minus 1 is negative 1. See down here? Oh, I shouldn't have put the parentheses. Sorry.
Okay.
Yeah, I shouldn't have put the parentheses. I'm sorry.
Where's the half bonding?
The 1. Because it's sharing 1 electron with it, right? For each oxygen. Okay? So now on the next structure, we're going to do its formal charges. Okay? So we're going to have S, and then we're going to star this O, and we're going to asterisk this O, because they're going to have different formal charges. Do you agree with that?
Yes.
Okay. So we're going to do star O and asterisk O. So let's do sulfur. Okay? Sulfur is 6 minus how many bonding electrons does it have? 6. So it's going to have a formal charge of 0, which is awesome because we like to be at 0 if we can. Okay, so this structure is looking pretty promising. Now we're going to do star O. Okay, so I've got 6 minus 4, because it's only got 4, and then minus 2, which is 0. So this one's going to have a 0, and this one's going to have a 0. Okay, so far I've got 3 of those at 0, which they like. It's better. Okay, so now let's do asterisk O. So I have 6 minus 6 minus 1, which is a negative 1, right? So this one has negative 1, negative 1, and so its overall charge is negative 2, which is what you need it to be. So this is actually the structure of SO4 2 minus. Okay? Did that make sense what we did? Okay?
So both of them add up to -2, but since they have more zeros...
Because they have more things with a formal charge of 0. You want it to be a formal charge of 0. That's the most desirable.
Okay.
Yeah, that's the most desirable.
I have another question is, how does sulfur get that many bonding?
Because it's in group, the third period, not group, it's in the third period, so it's able to expand its octet.
Okay.
Because it has D orbitals available to
that's
them.
Okay.
And if you want me to really blow your mind, I read something this weekend. I'm on like a group page for AP Chem, and first of all, there's some evidence that carbon can form more than 4 bonds, that it can form up to 6 bonds. I'm like, oh great, we're gonna have to start teaching them that. But that's still like very rare. And then you know how we've always said, okay, you fill the 4 S's before you fill the 3 D's because the 4 S's are at a lower energy level. That's actually not true. That's still the way we're going to learn it and teach it, but actually they've discovered that what happens is actually the 3D is a lower, but then we turn around and tell you, well, their valence electrons come from the S. Well, you're supposed to take the valence electrons from the higher one, not the lower one.
Yeah.
So technically what's technically happening is it's filling the D's, and then it jumps up and goes to the 4s, but it technically goes into the D's first. So I was like, dude, what are you doing to me here? So it's kind of crazy. Yeah, kind of crazy. And in the redesign, you're not responsible for the exceptions of chromium and copper. You are no longer responsible for those exceptions. Okay? If you did the exceptions, they're not going to count it wrong, but you're no longer responsible for them. Because we teach you that in Chem 1, which I'm going to do some thinking about that and see if I'm still going to teach those exceptions. Because if they're not tested on AP, I don't really need to teach them in pre-AP. Because they're learning more and more new things, which is why they took away the dehybridizations as well.
So they haven't found any where carbon is bonded
Yeah,
six times?
they have. They found a compound that does, or they think does. Okay,
Oh, they think that.
so this one, the next one for a formal charge, is going to. I'm going to let y'all do on your own, because it would take us a long time. So I want you to. I'm going to. Oh, I forgot. I thought I did that. So I'm going to challenge you with this one right here, the exercise 10. Okay? There's 3 different, I'm going to give you a hint though, okay? So you're going to do one with all single bonds. You're going to do one with 2 singles and a double. And then do one with 2 doubles and a single. And then I'm challenging you to tell me, based on formal charge, which one of those is the best structure. Yes.
What determines a good structure again?
The formal charges. You want your formal charges. So in this case, we have no charge on the XE03. So they need to add up to 0, all your charges. But the more things that have a formal charge of 0 and still add up are better. So like in that previous example, the reason the first structure wasn't as valid is because sulfur had a -2 and all the oxygens sulfur had a +2, excuse me. And then all the other ones had a -1. And then the second structure, we had 3 things that had zeros. That's better. Formal charge of 0 is better. Okay? All right, so let's move now. We did all this. It'll be faster if we move over here. Where did we end? Draw the Dang-Lewis structure. That's where we ended, wasn't it? Okay. So I'm going to have to stop it here because it's a different set of notes I need to open.